Okay, this is another video where we're talking about servos and the extension boards we use to power them. Um, Now, last time we talked about how the frequency of the PWM signal wasn't the right frequency. It's supposed to be 50, and then you're supposed to go from, for these servos, which are most of the servos, these are the servos I have, I go from um, 0.5 a millisecond pulse to a 2.5 millisecond pulse. And what we're seeing, which means that 1.5 would be the center. And what we're seeing here is that our frequency is 5.17, and our pulse, which is T plus, is 1.45 milliseconds, which does not get our servo to the center. And so you can see how this pulse works if I set it. Let's see if I can set this down. See if I can get it focused. If I set this to 0 degrees, you see 0.48 milliseconds, which is 480 microseconds. If we go all the way over to 180 degrees, what we're seeing is 2.42 instead of 2.5 milliseconds. So that is a problem. So how can we fix that? Well, we need to be able to adjust our pulse. And if we look at the extension that we're using, we can see that the frequency, okay, let me explain something else. These chips, these extension boards, all have certain chips in them, and this one is no exception. Right here, it has the chip, the PCA, I think it's 9685 chip right there to handle the servos. Right there is where it is. And that handles the servos. It can handle, this chip can do up to 16 servos, but probably because of constraints and wiring and whatnot, it only allows you to have 8 at one time. But the chip itself can do twice that. Okay, so this chip has inside it an oscillator. It's called an oscillator, internal oscillator, and basically that chip vibrates. And when that chip vibrates, it gives us electrical pulses back. And what we can do is we can use that as a clock. We can count how many pulses there are and figure out how much time has passed. And we can also use that to run our CPU or whatever else we need to do. Basically every computer has a little clock of some sort in it with some sort of crystal that vibrates. Now, the problem with these chips is that the crystal is so darn small that it's not very accurate. I have seen where it's anywhere from 23 megahertz to 27 megahertz. That's kind of a big range when it's supposed to be exactly 25. And you might say, well, what is the symptom of using the wrong frequency? Well, let's look at that. put our servo on here. Servo. Thank you. Let's turn it on. And you can see it goes to what it thinks to be 90 degrees. If we go to 0 degrees, I think that's 0. There's 0. We get it to go around like that. If we go to 180, it should be straight across from there, right? It's not. That's because the pulse width we need to get all the way around to 180 degrees is 2.5. But what we're getting is 2.4. So we're missing that. And when we go to center it at 90 degrees, it's slightly crooked off to one side because it's 1.4 instead of 1.5. So it's not. And because each chip is a little bit different, if you were to take this exact same board and swap it out for another one that's exactly the same one from the same manufacturer and everything, because those oscillators are different, you can end up turning your servos to different positions even though you're telling it the same number of degrees. So 90 degrees is going to be different for each one of these expansion boards because of the chip that's in there not having a perfect oscillator to use. Okay, so let's go back to our code and start looking through it a little bit. Now here's where we set the frequency, and the frequency is some number, and the math here. Hello, kitty. Sophie has joined us. There's Sophie. The math looks like this. You have your oscillator clock divided by 4096 times the update rate, which is the frequency. You round that and then you subtract 1. And so what is that actually doing? Well, let's try to explain. You've got a 25 megahertz approximately oscillator, and what you're doing is you're counting the number of oscillations per each step in the pulse width modulation. And we've decided that there are 4,096 steps in our oscillation. So you can start and stop at any one of those steps, and depending on which one you start on and which one you stop on and how many microseconds each one of those steps takes, you can decide how long that pulse is going to be. So there's a counter in there, and for each pulse, and our pulses are supposed to come at 50 hertz, which means 50 times per second, we divide that up into 4,096 pieces, and then you tell it how many pieces do you want that pulse to be on for, and then the rest it's off for. Now, this pre-scale value, I believe, doesn't say that this anywhere, but I believe that what it is, based on these calculations, is that that is how many oscillator ticks per every one of these 4,096 counts. So the chip is counting the oscillator, how many times that is ticking, using that to go to the next step in the 4,000 or so steps in the pulse, and that's how it works. So what we're really trying to do is come up with this pre-scale value, which is the number of ticks in the clock. And the reason why, so we've got this clock, And basically, we know that there's 4,096 steps, and we know that the update rate is like 50 per second, right? That's how many total steps per second. And given that this oscillator is 25 million mega, I think that's millions, of oscillations per second, we can calculate how many oscillations we need to count. Okay. Now, let's go back. Hi, kitty. So that is supposed to be this formula. That formula is supposed to be this. It's not quite the same. It looks a little odd. I'm not sure what they were thinking when they did this. They have an extra variable here from that. I don't know. They didn't do the rounding. It's probably doing a truncation because you're only sending a certain number of bits. The important thing to remember is you're going from 0 to 255, where the first 0, 1, 2 don't count because they're too fast for the rest of the chip. So from 3 to 255, that's not a whole lot of different numbers that you can choose from. It's not like you've got millions of numbers to choose from here, because that all gets boiled down into an 8-bit number. Is it 8-bit? I think it's 8-bit. So we want to do this differently. Now, first thing I did was I said, well, maybe I should be able to enter the actual value of this oscillator. And that was a good idea if I could figure it out. But the math is going backwards in the math is kind of silly, and because of all this truncation that's going on, you're moving little tiny amounts over and over and over again, and all of a sudden it flips and it changes because of the truncation. So what I decided to do was to go ahead and make it so that I could input a prescale value directly. So instead of calculating it, I'm going to have basically a block that says set prescale, and this will be a number between 3 and 255. 3 and 255. And that's just going to save that prescale as the count. Now, I have initialized it to 0. So it already starts out at 0. So if you don't call this function, it'll be 0. Now when I go to set the frequency, which I want to be 50, always, if the prescale hasn't been set, I'm going to set it to, based on these parameters, just like they are. And this is the correct way to express that formula exactly as they have it, by the way. Without a lot of, fooling around. One thing I have noticed about these extensions is that they're all the same code. Somebody wrote code for this at some point, and everybody else has just copy-pasted it. So there you go, without ever actually looking at it and seeing, hey, what does this actually do? Okay, so this allows us to actually enter the prescale amount. So let's go here, and this is our kitten bot, and this is the code that we were running. We were running this code before, with using the prescale that is being calculated. But if I decide I want to, I can set that prescale in advance to something other than what's being calculated, which is usually this 121. If you do the actual calculation, you get 121. Okay. It turns out 125 gives us a better result. So let's look at that. Let's turn this off. Let's plug it in. Oh, you can't see that. Yep, there's my kitten. Hi. Let's plug that in. Let's download it. And let's blow the plug on this for now. And let's put our oscilloscope back on. It's good to have an oscilloscope. These new digital oscilloscopes aren't that expensive. They're like $30. All right, let's turn that on now. And we're setting the prescale amount for us. Let's see if we can get that in focus. And as you can see, the frequency is 50.0. And you can see that the midpoint is 1.5 milliseconds. Let's go to 0. 500 microseconds. That's about right. Let's go to 180. 2.50. Okay. So now given that, let's replace this with a servo. Remember this servo? We weren't getting the full range out of it before. Come on. There we go. All right, switch that on. $90 degrees. There's 0 degrees. And let's watch that 180 all the way around. Go back to the center. There you go. So this is the full range. And given that we have it set so that 0.5 is 0 degrees and 2.5 is 180 degrees, any board that we use when we set it up that way is going to treat the servos exactly the same way. They'll go to the exact same spot given the number of degrees for any board as long as we set it up correctly. So what I've been doing, oh, that's upside down. Ta-da! I have been putting a little label on each of these boards to say what the prescale is. This one's 125. And that way, if I have a different board than this, I'll have the prescale at the bottom to make it act as the same as this board does, as close as possible. As close as possible. Now remember, we only have 3 to 255 different prescales to choose from, and so it's limited in that you have to use the one that's closest. So they might be a little bit different because we're just using the one that's closest. Let's look at a different board now. So in this case, let's see what we're doing. We're going to use this. Now this is the DF Robots version. This is the DF Robots version. And if you look closely, there's that same chip. PCA 9685 right there. So let's go ahead. Oh, you've already seen the prescale. Oh, okay. But let's do the exercise anyways. So you already skipped to the end. All right. Let's put this in here. And let's go in there. Sassy thing. All right. Almost as sassy as this cat sometimes. She can be pretty sassy. Coming back, okay. She probably thinks I should be feeding her dinner. Okay. Let's hook up. Hi, kitty. Hook up servo 1. I can look around the cat. All right. All right, this gets plugged in for power. Okay, excuse me, kitten. Thank you. All right, so let's get that focused. Frequency is 52.1, and our center pulse is 1.44 instead of 1.5. So that is not going to work quite the way we want it to. So what we're going to do now is we're going to come over here and we'll look at what I'm going to change. So remember that crazy looking piece of code we saw in that other extension? Here it is, exactly the same. Who copied from who? All right. So this is what I'm going to do. I'm going to do the exact same thing. I am going to create a prescale, set it to 0. I'm going to add a function to set the prescale count and initialize. And if the prescale is 0, I will use the calculation. But if it's not, I'm going to use the prescale count directly for this. So you've already seen what I'm going to be doing. And over here I have a list. I had a little list in that other one, but I didn't show it to you. These are the different values. So at 125 we're getting 40.5, 126 50.1, 127 49.7. So we're going to try 126 because it's 50.1 hertz. Okay, excuse me, kitten. Let's turn your better side to the camera. Can we do that? All right. So we can turn this off. Thanks for doing that. Let's see if I can get this in here. Helps if you put it in the right way. This is not a USB-C cable. There's one way to go in. All right, let's download that. Now, when we turn this on, and we look at, get that in focus, kind of, sort of, yeah. Okay, so we've got 50.0, 50.1, and it's kind of moving back and forth. That's probably not a good sign that it's moving around like that. This might be using an ultra cheap chip to do that. Let's go down to 0. We see we get 0.5 or 0.59. All the way to the other side, 2.48, 2.49, 2.50. That's about as best as we're going to do, because remember, it's we've got that rounding in there, and we've got, you know, only a certain number to choose from. Okay. So we can see with this one, are you chewing on cables? You know you're not supposed to chew cables, right? Let's see if I can get this to go on there. There we go. So here's our 90. See if I can get this to focus. So it goes to 0. And then all the way around 180 degrees, and then to the center. Okay. So as you can see, if we swapped out this completely different board for this board, as long as we have these set up correctly, the code will work. We'll just have to change all of the calls to the right extension, whichever extension we have in that we have loaded, and it should work. The angles of the servos should work. And as you can see, I've gone ahead and I put our prescale number of 126 on a tag so that I know what to set this to when I go to use it. Okay, so that's a little bit more about servos and these extension boards and how they work. I hope that helps in some way. Thank you for watching, and thank you to Sophie for helping us, and I will see you in the next video.